Welcome to today's conference call, Control of Cracking in Concrete. My name is Hilda, and I will be your operator for today. At this time, all participants are in a listen-only mode. Later, we will conduct a question-and-answer session. Please note that this conference is being recorded. And now I would like to turn the call over to David Darwin. David, you may begin.
Hi everyone. On behalf of the American Society of Concrete Contractors, I'd like to welcome you to the presentation today on control of cracking in concrete. I'm Dave Darwin. I'm a professor at the University of Kansas, and here at KU I chair the Department of Civil, Environmental, and Architectural Engineering. Okay, we'll just get started here. Okay, well, cracks reduce durability, affect appearance, and may represent a major structural problem. They can form in plastic concrete, is what they look like, and they can form in hardened concrete. And today what we're going to do is we're going to talk about the causes of cracking in both plastic and hardened concrete, and talk about methods of controlling cracks, and then we'll summarize. And I'm going to have a number of themes. First, we're looking for low cement and water contents, and side by side with that, we're talking about high aggregate content. Low slump wherever settlement cracking is a concern. High strength is not always good if you're concerned with cracking. Low temperature concrete, low evaporation rate, good curing, low reinforcing bar spacing, watch out for re-entering corners, and if you know you're going to have cracks, pick the crack locations. Okay, so let's first take a look at cracking in plastic concrete. And we'll be talking about settlement and plastic shrinkage cracking. And so first, settlement cracking. Settlement cracking occurs after concrete has been consolidated and finished. And what happens is the bleed water continues to rise, and at the same time the solids will continue to drop in the concrete. If you have a fixed object such as a reinforcing bar near the upper surface of the concrete will have to settle around it. And what you'll do is you'll develop tensile stresses in a material that really can't have tensile stresses, and you'll get settlement cracking directly above the concrete, or directly above the objects. Now, this has been well known for a long time. This is some really classic work by Dockhill, Caddy, and Carrier. And what they did is they had a number of test specimens where they cast small slabs of concrete with different values of cover. So we can see the cover ran from three quarters of an inch up to 2 inches. Bar size was number 4 through number 6, and the slumps ranged from 2 to 4 inches. And what we see is the cover had a big effect, and so if you wanted to have less cracking, this is on the vertical axis, we have the percentage of slabs that crack. If you want to have less cracking, that means you want to have greater cover. But also notice what happens is the bar size increased, and as the slump increased, the amount of settlement cracking that occurred also increased. Now, at KU, we've done a lot of work on bridge decks. And take here on the vertical axis, we have crack density. And we express crack density in linear meters per square meter of concrete. This dates back to the days when Kansas was a SI state. But I think if I told you had a half a meter of crack in a square meter of concrete, I think you all can picture that. And here, this is from bridge decks that were cast a long time ago, back in the 1980s when they used low slump concrete. So they had a range from, and this is inch and a half slump up to 3 inch slump, and you can see the relationship represented by the black bars, a big increase in cracking with an increase in slump. Now, one of the items here to keep in mind is that the higher slump also coincided with more water and more cement. So we did a statistical correction, and we found, though, that we still got an increase in the amount of cracking that we had on the bridge deck with an increase in slump. And so how do we improve or reduce the potential for settlement cracking? One is to get good consolidation. This is a procedure that's used in Kansas very effectively on bridge decks. And what this is vertically mounted internal gang vibrators. These are 1 foot centers before the finishing, before the roller screed, And Kansas, in general, has less cracking than our surrounding states, and we've been out surveying a number of different states. And one of the reasons we feel sure is the improved consolidation. The better the consolidation, the less settlement can occur later on. Now we actually can test this in the laboratory and see what different effects you can have. So this is a test procedure we developed at KU. These boxes are 12 inches square. They're 8 inches deep. We put a number 6 bar in there, and we have an 1 1/8 cover on top of that. And we fill these boxes with concrete in 2 layers. We consolidate the concrete, and then we look at the amount of settlement cracking we have. And this is an example we have. So on the vertical axis, you see the crack length divided by the bar length. So that means it's a 12-inch long bar. So if it says 0.5, that means the crack is 6 inches long. And we plot this versus slump. And so this is what we call a control mixture. There's nothing special that we did here to reduce settlement cracking. The paste content is 27%. Now 27% is a value we pick because that's sort of the maximum that we would want to have for our low cracking high performance concrete bridge decks. We usually want to be below that. At any rate, what we can see is just like Doc Hill had in his early test, that we get a clear increase with the amount of cracking as we increase the slump. So this is our control mixture. Now, if we do something, what can we do? Well, we've evaluated a number of different methods. I want to show you just 2: synthetic fibers and rheology modifying admixtures. So, and we've tested lots of different synthetic fibers. I'm just showing you one comparison. They all perform quite similarly. Notice here we had 3 pounds per cubic yard. This is a macro fiber. F1 is just a code number. And what we can see is we have considerably lower amounts of cracking even at the high slumps. As a matter of fact, even at an 8-inch slump, we have less cracking than we did at a 2-inch slump for the control mixture. So the fibers did a lot to reduce the amount of settlement cracking. We also have looked at rheology modifying admixtures. You see, they also give you an improvement. Now you can say, well, not as much an improvement as the fibers, but I want to point out that if you're operating with a rheology modifying admixture and you're down here at a 2-inch slump, as soon as you put a vibrator in it, or when you put it in a pump, it's going to behave like it's a 4 or 5-inch slump. So when you work it, the rheology modifying admixture makes it much more workable, and then the concrete stiffens up. Okay, now, so what can we do for settlement cracking? Well, we can use lower slump concrete. We can increase the cover. We can use a greater number of smaller bars, because we saw earlier bigger bars give us more settlement cracking. We can thoroughly consolidate the concrete. We can use fibers, and we can use rheology modifying admixtures. We're also in the process of looking at other methods to reduce settlement cracking, and we'll be presenting those, not in this presentation, but those will come out in the in future days. Okay, how about plastic shrinkage cracking? Well, plastic shrinkage cracking occurs when water evaporates more rapidly from the concrete than it's resupplied by bleed water from underneath as the bleed water rises. The settlement cracking is not very deep. Here's an example of a pavement with significant amounts of settlement, not settlement cracking, but of plastic shrinkage cracking. And when you get plastic shrinkage like this, there's not much you can do right there on the job. You've kind of lost it. If you just have 1 or 2, you can put a 2x4 and smack it with a mallet and close it up. But you cannot trowel over plastic shrinkage cracking. They will reflect up through whatever any amount of cement paste that you've used to cover up the crack. So and here's another example of a settlement crack. So the typical procedure and the guidance that you have here is there's this nomograph that I think many of you would be familiar with. This nomograph is available in textbooks and ACI and a number of other and PCA publications. And what you do is simply start off in the nomograph knowing the air temperature. You slide up here to the relative humidity. You go over to the concrete temperature. You drop down to the wind speed, and you come over and you get a rate of evaporation. A general rule is you want a rate of evaporation of no more than 0.2 pounds per square foot per hour. But if you have a low bleed concrete, such as one with silica fume in it or fly ash, then you may want to be closer to 0.1, a rate of 0.1 pounds per square foot per hour. So what can you do about plastic shrinkage cracking? Well, you can put up something. You can reduce the wind by using windbreaks. Cool the concrete. That's always good for many reasons. Cool concrete doesn't set up, so and even in hot water nearly as fast. You can use evaporation retardants. Use an early bleeding water reducer, and you can start curing early. That is, never let the concrete dry out. So if you have a job where you can actually have burlap on it, and it's not going to affect, you don't care about the surface being, you don't have to get in there and trowel it, then this works very well. Yeah, about hardened concrete. Now, there's lots of causes of cracking in hardened concrete. The ones we're going to cover today are the ones that are underlined. So we'll talk about drying shrinkage, cracking, cracking due to thermal stresses, poor construction practices, and errors in detailing or design. And I'll have a few examples of those for you. Okay, so let's start off with drying shrinkage cracking. This is the one that really kind of dominates construction and most concrete. So when you say concrete cracks, it's likely going to be due to this. Okay, and the problem is this right here. This is just cement and water. This is cement paste. It's a little patty. It was placed on a piece of glass and allowed to dry. And just the friction between the cement paste and the drying and the glass is enough to cause it to crack. So this is the part of the concrete, the cement and water, that causes shrinkage to occur. Okay, so what we have is, if we start off with the original, whatever concrete original length, if it was unrestrained, that means if it was totally greased up, if we could slide easily, we wouldn't have any cracking. But there's always some restraint. There's the reinforcing bar, there's other parts of the structure, there's the subgrade when we have slabs on grade, and because of that restraint, concrete gets placed in tension, and we know the concrete is not strong in tension, so we have the cracks forming. So if we had an opportunity to place concrete on slabs on grade, and we had rollers underneath it, then we wouldn't have cracks, but of course we don't. And we've got the subgrade, we have significant friction at that point, and so we have cracks that are going to form in the concrete. And in this case, the main thing is we want to do is control the location of those cracks and make sure that, and have people not think they're cracks. Okay, now this is a demonstration, a series of lab mixtures that we did for the purposes of demonstration to show the effect of the paste content, that is the water and the cement, on the amount of cracking, or excuse me, on the amount of shrinkage that you have. So on the vertical axis, this is free shrinkage. It's in the units are microstrain. That's the change in length divided by the original length multiplied by 1,000,000. And this is time. This is the days of drying. So we went out to a year. And we did three really sort of series of mixtures. This is 40% cement paste, this is 30% cement paste, and this is 20%. This is much lower than you'd ever have in practice, but you're going to be operating, most times you're going to be operating in this region in terms of percentage of cement and water that you have in terms of volume. And for each percent of cement paste, we also had a different water cement ratio. Now, over in the legend, the order of the items in the legend, of the different mixtures in the legend, is the order that you see as we go down from the top to the bottom. And so one of the things we observe is, first, the water cement ratio. A lot of people think water cement ratio controls everything. Well, it doesn't. It has a big impact on strength, but it certainly doesn't control shrinkage. And we can see that water cement ratio is not the governing factor. It's just how much cement and water together we have. Also, if you want to take a look at this, you'll see in each case, if we take a look at the shrinkage out of 365 days, that it's the highest water cement ratio in each case that has the least shrinkage. Now, the reason for that has to do with the fact that the pore system, higher water cement ratio, bigger pores, actually less stress to cause shrinkage. But even here, the effect of water-cement ratio is relatively small compared to the effect of paste. So extra water and extra cement together will hurt you. Okay, this is bridge decks. We do a lot of work on bridge decks. I just want to show you a few things. And this will show you one item in this case. This amount of cracking that you see is the average amount of cracking that we have in some of our better performing decks that we don't use high performance crack control on. But this is pretty typical of a deck in Kansas. And one of the things we learned here has to do with strength. So this is a plot similar to what we had before. On the vertical axis, again, is the crack density in linear meters per square meter. And now if you take a look inside the parentheses, this is the compressive strength of the concrete as measured by standard cylinders made on the job site. And this we go for a nominal strength of 4,500 up to 6,500 psi, and you see we triple the amount of cracking. Now all the concrete on these jobs were specified at 4,000 psi, but we know we have all sorts of variations out there. People, folks are going to hold back water. They want the concrete to get early strength. We can see that high strength is not going to be a friend to you if you have a highly restrained piece of concrete that's going to undergo shrinkage cracking. Now, what's happening here? Well, it turns out that high strength concrete creeps less than low strength concrete. Now, that's great on a high-rise building. We're using high strength concrete in columns. You don't want those columns to shorten up, and you want to limit how much they shorten up, so you want low creep. But when the concrete's being placed in tension, as it is in a bridge deck, creep is good because it helps relieve the stress. So that's why high strength concrete is not something that we're looking for if we want to have crack control on highly restrained concrete. Yeah, how about admixtures? Well, there are some admixtures that are specifically designed to help us out. These are shrinkage reducing admixtures. They can reduce shrinkage by up to 50%. And what they do is they reduce the surface tension of water. Now, the surface tension of water down in the pores, as the concrete begins to dry, the surface tension in the water within the meniscus inside the pores tends to draw the surrounding concrete in, and that causes the initial shrinkage. So that's how shrinkage-reducing admixtures work. The one thing we need to be aware of, though, is that air entraining agents also reduce the surface tension of water. And if you add a shrinkage-reducing admixture, you'll end up with larger air bubbles, which can reduce the ability of the concrete to withstand cycles of freezing and thawing. Okay, here's an example of what happens with shrinkage-reducing admixtures. So you can see here, this is a control mixture for this is the first 30 days of drying. All the concrete that you see here, this was actually wet cured for 14 days, and so we're looking at the drying time here. And you notice they all give a negative value of shrinkage means the concrete has expanded a little bit, so we had some swelling, and they all had swelling about the same amount. And then the control mixture has the highest amount of shrinkage. And then we have one dosage of SRA, or shrinkage-reducing admixture. We have less shrinkage, and even a higher dosage, we have less shrinkage. So this is what happens if you use a shrinkage-reducing admixture, and they're ideally when there's no freeze-thaw, or the modern shrinkage-reducing admixtures. Many of them work quite well under conditions of freezing and thawing. Okay, now water reducers and superplasticizers. I have them up here not because they're part of crack control, but they will not hurt you or they will not help you. It's just how you use them. So, for example, if you use a superplasticizer and then can go for a high slump, that's fine. But if you have settlement cracking, the high slump from the superplasticizer is going to have the same negative effect as if you just had extra cement and water. But in themselves, properly used, water reducers and superplasticizers will not impact the amount of cracking you have. Internal curing. Now, this is a good way to help reduce the amount of shrinkage that you have and resulting cracking. And so, what I have here is another example. Again, this is on the vertical axis. Again, you see the amount of free shrinkage that you have. Up at the top, this is your control. This is nothing special. And then the internal curing, what we do is we have pre-wetted lightweight aggregate. And when you say 10%, that means 10% of the volume of the total aggregate was replaced with a lightweight aggregate. This was saturated lightweight aggregate. And you can see the internal water, as it came out inside the concrete, helped reduce the amount of shrinkage. Now, this with the water-cement ratios in these particular, or water-cementitious material ratios in these cases, were not particularly low. So there's not internal curing has separate advantages for really low water-cement ratios. But in this case, the water-cement ratio was 0.45, so very regular material. We don't have to worry about something called autogenous shrinkage. But you can see the water coming out helped a lot. And then what we had is we combined that lightweight aggregate now with a replacement of cement using slag cement. And this is a 30% volume replacement of slag cement. We got an additional reduction. And finally, we had another replacement of cement with 3%, again by volume, with silica fume, and then in addition to the 30% slag, and had another boost. And so you can see what we have here is we have the synergistic effect. They all seem to work together and help reduce the amount of shrinkage, and in turn the amount of shrinkage cracking that you're going to have. Shrinkage compensating concrete has been around for a long time. There are different types of shrinkage compensating admixtures. Type K cement is probably the oldest in the U.S. in our practice. Now we flip things over. Shrinkage is down and expansion is plotted up. But what happens is the idea is that you have an expansion in your concrete because you've got a shrinkage reducing admixture, or the cement is the shrinkage reducing cement. And then what happens is as it begins to dry, it then shrinks just like regular concrete. Well, here is regular Portland cement concrete, minimal expansion during curing, and then it shrinks. The two shrink about the same amount. The trick is, what do you do with this expansion to help you out? And what you do is you have to have internal restraint. And so we do that with reinforcing steel. You balance the amount of reinforcing steel. As the concrete expands, the reinforcing steel is placed in tension. Because the reinforcing steel is restraining the expansion that occurs from the admixture, the concrete itself is placed in compression. And then once the concrete begins to dry, everything shortens up. But the steel acts like a spring, and it keeps the concrete in compression. And so this is the whole theory behind shrinkage compensating concrete. And so you actually have to have a balance between the amount of steel and the amount of expansion that you have. Here's an example of what happens, and this is a little bit different. What we're doing in this case is we're looking, this is shrinkage versus time. It's negative. That means it's swelling. And so what we're doing is, instead of waiting a while the concrete cures, we're looking at what happens immediately after we cast the concrete. And so what? At 5 hours, just after initial set, we start taking our measurements. And so here's the controlled concrete, nothing special is happening. And what you notice is there's some expansion. We already noticed there's expansion, about 50 microstrain expansion. Now we have two different shrinkage compensating admixtures added, and notice that they give us some action right in the first couple of days. Now these are different kinds of admixtures. In this one we have most of the expansion has occurred by about 3 days, and then it remains approximately constant. We don't get any more expansion. Whereas this other shrinkage reducing admixture continues to expand over time. Now there is another difference. This shrinkage reducing admixture also includes this shrinkage compensating admixture also includes the shrinkage reducing admixture. So we're going to see some difference after we allow drying to occur. So now we've expanded the time scale. This is the expansion that we saw. Cure these for 14 days, and now we're letting them dry. Notice with this particular what we call SCA2, that the amount of shrinkage is about the same as we have with the control, except we're down here and we still end up at 30 days. We end up with essentially no net change in length. The SCA1, because it also includes a shrinkage reducing admixture, its rate of shrinkage after we allow drying it occurs more slowly. Okay, what not to use? If you're concerned with cracking, calcium chloride is not a good choice. It increases shrinkage, decreases the long-term strength, it causes corrosion of reinforcing steel, and it discolors the concrete. So completely separate from cracking, it's not a good choice to use on architectural concrete. Okay, let's talk about construction procedures. Key one here is curing. The trick is never let the concrete dry out until you let it ready to dry out. Now this is a bridge deck, so we're not interested in getting a good hard trowel finish on this. We put 18 wheelers over it, and we're actually going to come back and we're going to come back and groove this later. But what they're doing is right after finishing the concrete, and actually you see the finishing equipment is sitting right here. They're getting wet burlap right on it, pre-saturated wet burlap. Here's an example, very efficient, very low-cost way to do it. This is all pre-saturated, fully saturated. You never want to put dry burlap down on wet concrete. Don't expect the bleed water to get you the curing. Fully saturated. It's a three-person crew. You can see there's one down here, there's legs, the other two guys here hauling it across. Very efficient. It's all pre-cut. They can cover this concrete up in under 10 minutes. They can put the second layer down within another 5 minutes, and they get extremely good results as far as curing. Plastic shrinkage cracking doesn't exist on bridge decks that are constructed this way. Next thing is you keep the concrete wet. You just don't let it dry out until you're ready to let it dry out. So they're keeping it wet until the concrete is fully set, and then they typically, if you want to get it right, you put soaker hoses and you put the plastic on it. Now, other methods of curing. Here's another example: putting a sprinkler on burlap. Putting plastic on the concrete. Of course, this is going to affect the appearance of the concrete to some extent if the plastic comes in contact. Here's an old slide from PCA using waterproof paper on a paving job. More likely, you're going to see a curing compound being sprayed down by equipment, getting a nice good coverage. A lot of times we see this. This is not unusual at all. Take a careful look, and you see that although he's getting part of it covered well, he's not getting the whole thing covered. Now, one thing to keep in mind about curing compound or surface sealers like this is they do not stop evaporation; they slow it. So it's better than nothing, but it's not going to be as good as if you can actually keep water on the surface of the concrete throughout the full time of curing. Why is curing so good? Curing cuts down on shrinkage at early ages, and it also ties up water. So the key thing here is that the first time concrete dries out, the hydration process stops. After that point, it's not going to start up again if you re-wet it. So I said it twice already. Don't let the concrete dry out until you're ready to let it dry out, because it's not going to start rehydrating again, at least not right at the surface. And we actually get a little bonus here. Okay, this is two concretes. This is wet cured. This is 7 days wet curing. This is 14 days wet curing. The difference here, around 25 days, is on the order of 50 microstrain. You say, well, what's 50 microstrain? Doesn't look so much. Well, that's 200 psi in the concrete. And if you have 200 psi in the concrete, that might be the extra psi due to shrinkage stresses. That might be the difference between cracked concrete and uncracked concrete. And by the way, let me point out, this is a low shrinkage concrete, 23.3% paste. Check out the cement content. So this is a very low shrinkage concrete to begin with. Extra curing definitely helps out. Okay, detailing. Let's talk a little bit about detailing and design to control shrinkage cracking. Okay, slabs on grade. Lots of you, I'm sure, work on this area. If we don't, in this case, we know we're going to get cracking, and the trick is for us to select the crack locations. And clearly, there was nobody selected any crack locations here. So what do we do? Typically, well, what we want to do is we want to put in contraction joints. The rule is to cut the depth 1/4 the depth. There's some methods that we can actually go a little less because we can get there early. get on there earlier. But the key thing here is you need to have, the reason that typically we say a quarter of the depth is we want a real weakened plane so that the concrete will crack at that location. Concrete is variable enough that if we put a very shallow groove in here, we use our saw and cut at a very shallow depth, that might not be the weakest point in the concrete. Now here's a good example we looked out. Here's a slab where they did not cut 1/4, but it was still, in this case, turned out to be weak enough to get the weakened plane formed there, and we got the crack. To the owner, this is not cracked concrete. It's nice and straight. Also we can fill up. We can fill up. This is a joint. We can fill it up to protect it from getting dirt and dust in there. But if this is not cracked concrete. Okay, re-entrant corners. Anytime we have a slab where there's a notch in it, like we see here, we're going to have tensile stresses right at the tip of that notch, and we're going to get a crack that's going to form there. Doesn't matter if it's slab on grade or if it's structural concrete. It's going to form at that location. So in this particular case, the design was not appropriate because the joints should have aligned with this notch, and therefore we wouldn't actually have had a solid concrete that decided it wanted it to crack because of going into high tension. Okay, so the way we do that, we use layout. We put in our contraction joints. The general rule: 24 to 36 times the slab thickness, less than 18 feet, recommended by ACI 302, Committee 302. And we also make sure that we isolate our slabs from any structural elements such as columns or from the walls. So the concrete, when it changes volume, doesn't go shoving. Either due to temperature or moisture conditions, doesn't go shoving into the columns or the walls. So here's a nice little diagram from Committee 302, and we see this actually in a number of different ACI documents. We see this how the layout, and here's an example. So here we have isolation joint. Now this is not a contraction joint. This is we put a soft material here. Notice in both cases. Notice that the joint is laid out so that there is a re-entrant corner, but it actually lines right up with the contraction joint. So we're not going to have that high stress at any location. In this case, since it's circular, it's around. We have a round region in this case. Again, we're not going to have a re-entrant corner. And this is a shot of what it looks like from the side. So we have a fill material. There's an actual isolation of our column from the surrounding slab. So to protect or to control shrinkage cracking, what we want to do is we want to protect the plastic concrete itself. We don't want to give a place for cracks to start. Ideally, we want a material that has minimal amounts of volume change. So that means high aggregate and low cement and water. We can consider shrinkage reducing admixtures and shrinkage compensating admixtures. Cure the concrete well and use contraction joints as appropriate. Okay, how about thermal cracking? Okay, thermal cracking is a problem that occurs upon cooling. You have hot concrete that's restrained, and it can be restrained internally. I say mass concrete, the inside is not going to cool as fast as the outside. Or we can have restrained slabs, and here bridge decks are a big deal. And so anytime you put hot concrete on a cold girder, and the girders are always cooler than the concrete, unless you've gone to the trouble of heating them, you're going to have a problem with thermal cracking, because as the concrete contracts, as it cools, it's going to go into tension. Okay, so here's a plot. This is temperature rise versus age. This is for mass concrete. So if you take a close look, the cement contents are really, really low. But this is like for a dam. And this is work by Don Hooten, really famous fellow in the field of dam construction. What Don did, this is many years ago, and what you see, this is temperature rise plotted versus age, as we said. And so he started with 306 pounds and no pozzolans, and he gets a very high temperature rise over a period of time. As he decreased the cementitious material content and increased the pozzolan, relative pozzolan content, you see this drop here in temperature. That means the differential in temperature between the inside and the outside of the concrete in the dam is less, and therefore you have less effect of the higher temperature because the temperature just never got so high. Another thing, we like to start off with cooler concrete to begin with, because the cooler the concrete starts, even whatever the environmental conditions, the less total heat it generates. It reacts more slowly, which is good, and the total heat that it generates is reduced. So this is an example where they're cooling outside of a drum of a ready-mix truck. Here they're putting chipped ice in the concrete and replacing part of the mixed water with the ice. Here they're using liquid nitrogen to cool. There's parts of the country that if you want to cast concrete during the summertime, you are going to use liquid nitrogen just to get the temperature down, so you have a few minutes to get the truck out there and cast the concrete. So to control thermal cracking, we want to have a low cementitious material content. That generates the temperature. Pozzolans or slag always generate less total heat. Increase the size of the coarse aggregate. That's a way to get a lower cement and water in there. High coarse aggregate content ties in with that. General rule, cool the concrete to 60 degrees or below for mass concrete and to 70 degrees for structural concrete. And in case of when you're working with dam concrete, mass concrete, you have the ability, you can put a higher quality concrete right on the surface. So here we're talking about hundreds of thousands of cubic yards placement. The higher quality concrete goes on the surface. It can take the higher tensile stresses. Okay, let's talk a little bit about structural concrete. Okay, in walls, this is you have penetrations in walls. You have re-entrant corners everywhere when you put windows and doors. You're going to get these cracks, and they're going to form no matter what you do. The trick is to keep them nice and closed. Well, what you do, the requirement ACI tells you, just run 2 number 5 bars across in both directions, top and bottom. If you have 2 layers of steel in the wall, and run 1 number 5 top and bottom, or top and horizontally and vertically. To intercept the cracks, it keeps them nice and closed and prevents them from running out so far. If you have walls, the wall is going to be restrained by the foundation. It's going to shrink. It's going to tend to crack if it's very long. So the general rule is that the length of what you do is you put in a contraction joint. The general rule is that the distance between contraction joints should be somewhere between 1 and 3 times the height of the wall. Also, this is from this PCA slide. If you have walls, exterior of a building, there's recommendations on where to put the contraction joints in the wall so that it looks nice and straight, and it doesn't look like if it's straight like this and you pick the crack locations, nobody's going to think it's cracked. Okay, here's an example of a case where it's an error in structural design. Okay, so this is a reinforced concrete beam. If you look carefully here, there's crack that's running diagonally, okay, from upper left to lower right. We look at the other side, and the cracks are running in the other direction. Okay, upper right to lower left. Here's another one here. What did they do wrong in this case? Well, this was an industrial construction. They did not analyze it correctly, and what happened is they ended up getting twisting or torsion in the member, and they didn't design for it, so they didn't have adequate closed stirrups in the beam, and therefore the cracks just opened up and we saw them, and actually the strength was not adequate either, and there's quite a bit of retro work that had to be done here. Here's another example. This is pre-stressed concrete, what we call adapt-in beam. This is very popular precast construction, but it's got a re-entrant corner. So to be designed properly, it's going to have the tendency to crack. You've got to have reinforcing steel in the design to intercept those cracks, keep them nice and tight. Flexural cracking. There's often a lot of attention in structural design to flexural cracking. Rarely is this ever a problem having to do with strength. It's unsightly, but owners don't like to see big cracks. And so what we would like to have is we would like to have nice narrow cracks. And so what we know a lot about it. And so what we know is the crack widths for bending flexural cracks. Crack widths are going to increase as the cover to the center of the bar. So we have more and more concrete on the outside of the bar. The higher that cover, the wider the crack. As the spacing between the bars here, spacing increases, we're going to have wider cracks. And clearly, as the stress in the bar increases, the crack is going to open more. Okay, well that's handled in design, and there's actually rules in the ACI building code on how to handle it. And so here, this is the working stress, 40,000 psi. This would be for a grade 60 or 60,000 psi yield strength, and ACI gives specific rules based on the amount of clear cover you have, what the spacing of the bar, what your bars can be. So if you had 3-inch clear cover, you run over here, you're going to have maybe 7.5 inches. Spacing is the max inch you could have. This would be grade 40. This is grade 75 steel. Okay, also, if you have deep members, it's important not only to have close spacing on the reinforcing steel on the tension side, so this would be tension on the bottom, this would be tension on the top of the beam, but you also, one of the things that happens, you're still going to have cracking. Closely spaced reinforcement make sure that you have lots of very narrow cracks that's very difficult to see. Those are the hairline cracks. But if you don't do something, if you have a deep member, and that's defined as a member that's 36 inches or more, if you don't put crack control reinforcement along the side of the webs, those narrow cracks that are formed down here on the side will coalesce into very large cracks. So the ACI tells you that if you have deep members, you also have to have skin reinforcement, and that skin reinforcement, the spacing rules on the skin reinforcement are the same as the spacing rules on the reinforcement right on the tension surface. So to control structural cracks, we need to design for the loads, and we need to use low reinforcing bar spacing. Okay, so that brings us to the end. We talked about the causes of cracking in both plastic and hardened concrete. We talked about controlling cracks. And we had some themes here. We want low cement and water content. We had high aggregate contents, low slump where settlement cracking is a concern. High strength is not good. Low temperature concrete often pays off for us. We want a low evaporation rate if we're going to have a concern where we have plastic shrinkage cracking. We want good curing, low reinforcing bar spacing, watch out for re-entrant corners, and we want to pick our crack locations. And so at this point, I'd like to open it up for questions. That's the Kansas Jayhawk, my favorite bird. Okay, so if you got any questions, now's the time.
Thank you. We will now begin the question and answer session. If you'd like to ask a question, please press star 1 on your touch-tone phone. If you wish to be removed from the question queue, please press the pound sign or the hash key. There may be a delay before the first question is announced. If you are using a speakerphone, you may need to pick up the handset first before pressing the numbers. Once again, if you have a question, please press star 1. We have a question from Holly Christensen from Tom Ralston Construction.
Hello?
Hi, Holly. Hello.
This is Tom Ralston. Holly just set this up for me. Thank you for the presentation. I appreciate it. I learned quite a bit that I didn't know, and I'm a third-generation concrete contractor here in Santa Cruz, California. What we drifted into a lot Dave, is high-end interior floors that are only 2 inches thick, and the trend out here in California and Silicon Valley and Los Angeles has been to go with as few joints as possible. So our hat trick has been to try and produce as much a crack-free floor at 2 inches thick in a seamless fashion where we don't have any joints. So we go around all these reentrant corners, and we're using flat wire mesh. We're using admixtures like Tetragard or Eclipse. We're keeping the cement to water ratio fairly low. We don't add water. We only add what is called as ADVA. I believe it's a super plasticizer. And we cover all the lights in the house. We cover everything and make it as dark as we can, like a mushroom plant. And then we proceed to hydrate it with hand methods where we take backpack sprayers and we go through the floor 6 to 7 times a day for 7 to 10 days after the pour. So hearing that, Dave, is there anything else that we could possibly do? I mean, we do get a few cracks, but we've been fairly successful with these techniques that I've employed over the last 7 to 10 to 15 years.
Is this Tom? Is that right?
This is Tom Ralston.
Okay. Yeah. Okay, Tom. Great question. That sounds like you're using a lot of the technology that's out there right now. It's 2 inches. You're kind of right on the edge there, but you're using super plasticizer. You're using shrinkage reducing admixtures. You're minimizing the rate of evaporation. That's one point I want to get back to. Anything you can do to slow down the drying is going to be a plus for you, because we know that even high shrinkage concretes will be much less likely to crack if you allow them to dry very, very slowly. So anything you can do to delay the drying on the concrete, but still let them dry.
Yes.
To slow the rate of drying allows them to creep. So, for example,
right.
You're not doing this, but let's suppose you ponded it with water.
Right.
And then you say and then all of a sudden let it dry out. Not a good choice. What you want to do is if you're spraying water and it sounds like that. So that's not going to totally prevent it from drying, but it sounds like you got very slow drying, which is a real positive.
Right, and we use as big an aggregate as we can, 3/4 inch, and we usually we'll pump that at a line pump. We don't use anything less than 3/4 if we can get a little bit bigger aggregate. But one of the things that I liked that you said was that you vibrated your concrete in Kansas, and you've gotten so many less cracks because of the vibration and the consolidation.
Right.
I don't know that our cracking is due to that settling so much, but would you recommend, just hearing what I've been saying, that we too use vibrators, maybe have a couple of them going at the same time immediately before rotting off or immediately after?
Yeah, anything you can do to get that settlement to occur deliberately rather than after you do the finishing. So while the concrete's still plastic, that's what the good consolidation is for. So that's very on any project. Good consolidation.
So that I'm being redundant here, Dave, but yes, you're definitely encouraging us to go ahead and use the vibrators on our slabs. And then my second part of that question would be, what about the old tampers or the jitterbugs and the hand tampers that people have used over the years compared to the vibrators?
Okay, I don't like jitterbugs at all, and the reason, and I said some folks may swear by them, but I don't like them because they end up knocking the coarse aggregate away from the surface. And what you really want is you would like your concrete to stay as uniform as possible. Now, lots of times you put in a hard trowel finish on, you'd like to have paste up at the surface. You actually need it, but you want to have the minimum that'll work for you, because you want the coarse aggregate as close to the surface as you can, because that coarse aggregate's not going to shrink. And if you actually have forced the coarse aggregate down, that means you have a layer of mortar on top of probably pretty high quality concrete down below, and that mortar is going to shrink less, and so right away you're going to set up a differential volume change. Okay,
and you wouldn't think then that the vibrators themselves allow some of the heavier aggregates to settle, or?
Well, but you don't do all your slabs at 2 inches, do you?
No, we don't. But we are one of our specialties are these floors, and they've been buoying our company to a certain extent, and we do pretty well with them. So I'd like to continue to hone in on the efficiency and increase our success as we can.
Right.
On those. Yeah.
Okay.
Anyway, well, thank you very much. I'll let the other guys ask their questions.
Thanks, Tom.
Okay.
As a reminder, if you have a question, please press star 1. We don't see other questions in queue. Oh, I'm sorry. We do have a question from Denise Evans from Reliable Concrete.
Hi. Thank you so much for that great presentation. I am a sales rep for a manufacturing company that makes wet curing blankets for curing vertical and deck applications on bridges. And I learned a lot about the shrinkage process, which I need to know, so I appreciate that. I am curious. So you highlighted the burlap method of curing on bridges, which of course is something we're very familiar with. We deal a lot now with specifications. We're a national company, and specifications where they're specifically asking for a 7-day or a 14-day wet cure using wet curing blankets versus burlap. And I just wanted to know your thoughts on the curing process as far as the strength is concerned for what you're talking about and for reducing shrinkage and cracking on bridge decks.
Okay, good question, Denise. There's a couple of things here. First, whatever procedure you use, whether you're using blankets or burlap, and I can't emphasize this too much, it's got to be fully saturated when it goes down. I know there are some applications for both burlap and blankets. People think that the bleed water on top is going to wet it. It's not. If you put anything down dry, it's going to suck the water right out. And I'm sure you try to tell all your customers to make sure that it's fully saturated. The key difference, it all depends how they handle it. But a key thing with burlap is that for burlap to take, or for you to have the full advantage of burlap, you must have soaker hoses running all the time. And ideally, example in bridge decks, you'd also want to cover with plastic to lower the evaporation rate that you would have. The advantage there is that you do have a supply of water all the time. Generally, with blankets, you get the blankets fully saturated, and you're not going to be able to add any more water. Can you re-wet your blankets?
We can. We
over
have
time?
a perforated top for a vertical and bridge application. Each of our rolls holds the rolls are like 8 feet by 150. Each roll holds about 55 gallons of water. So we can resaturate, but we're finding, we've been using it on bridge decks across the country for a long time now. So we're finding that we don't need to resaturate, but if we had to, we do have perforation, so we can do that. Okay, well, I think that would be the key thing. I have not specifically done any research comparing the degree of curing, but we do know that some blankets will tend to dry out with time, and that's the key thing is ideally you'd like to if you dry out the top of the blanket, no problem, but the trick is you want to keep water in contact with the concrete for the full curing period. Okay, great. Yes, that's what we do, and I just was trying to get some feedback. I like to be able to have different things to tell my customers, so I appreciate that. Okay, thanks for the question. Mm-hmm.
David, this moment I'm not seeing further questions. Let me just do a quick reminder. Please press star 1 if you have any last questions. We have a question from Lowell Bry. Please go ahead.
Yeah, actually it's Lowell Brakey, Brackhard Concrete Construction Company in Dodge City, Kansas.
Hi, Lowell. You're not too far away.
No,
How are you doing?
I'm not. We're just about in the middle of the U.S. here. Anyway, my question, this is the first one I've been able to attend from the comfort of my office and my chair. I'm curious, how many of these have been done that involve the University of Kansas so far in this format?
Oh, are you talking about presentations?
Yeah.
Okay. Well, this is the first webinar. I've spoken at ASCC
I
a
believe
couple
you
of
have.
times.
Yeah. I normally
is the
attend
first
the
one.
World of Concrete or whatever. Yeah.
Yeah, it wasn't a World of Concrete. Actually, it was ASC separate meeting. But
So
this is the first time
Okay.
on a webinar.
Okay. I might mention that one of the reasons I attended this is the cities of Dodge City and Garden City require learning credits, and they've agreed to accept this web seminar as a 1-hour credit,
Oh, it's great.
which is very helpful since I can do it here from my office. I am curious if you have any scheduled more for this year.
Well, I don't have any schedule with ASCC, but there will be probably, I think we got 3 presentations, and we haven't scheduled the time yet, but with the American Concrete Institute.
Oh,
so
good.
So ACI, and that's clearly credits involved there. So
Yeah, we belong to that too, a lifelong member.
that's great. And
Hopefully
so
they'll do the same program. Okay.
that's right. So thanks for all your interest and everything.
I am. May I, just out of curiosity, or is this something we'll know later, may I ask how many people were able to attend this first format for you? Do you know as of yet?
I think there were around 40.
40.
I think so.
Well, this has been, like I said, has been mentioned by other participants. I found this enjoyable. I even ran across a couple of words I wasn't even familiar with, which was surprising. And so I thank you very much for that.
Okay, thank you, Noel.
And good luck on your program. I'm looking forward to more. Bye.
Okay, thanks so much. Okay, I think that brings us to the end. I want to thank the 3 folks who asked the questions, Tom, Denise, and Lowell. And I want to thank you all for attending. I enjoyed putting this together, and wish you all the very best.
Thank you. Ladies and gentlemen, this concludes today's conference. We thank you for participating. You may now disconnect.